So this is not a presentation. Instead, it's an experimental workshop/discussion entitled Demystifying Inter-Blockchain Communication. Because I've discovered, when talking to some people, they seem to be a bit mystified about inter-blockchain communication. So I'm going to try to wave my hands, do some sorcery, and demystify it. First, a quick survey. Who has heard of Cosmos? Who's heard of Tenderness? Just put your hand down if you haven't heard of the thing which I keep saying. Who's heard of IBC, Cosmos IBC? Who has heard of channels in Cosmos IBC? You can tell me what they are. you wrote it, you don't count. All right, thank you. So it sounds like I don't need to explain Cosmos or Tendermint too much, so I won't. Except for two sentences. In two sentences, Tendermint is a Byzantine fault-tolerant consensus engine that does not have the foolproof histories of things Solana talked about. So now I want to try to integrate that. But it does have, it's theoretically maximum fault tolerance to Byzantine engines on a network, and can provide finality under a partially synchronous network, which is a very reasonable model in practice. Tendermint is used to operate the Cosmos Hub, which we expect will be one of the first blockchains in the hopefully many blockchain Cosmos network. The Cosmos Hub was launched late this spring and has been operational with a bonded stake system since then, with no major bugs to my knowledge. And IBC is the inter-blockchain communication protocol, which is my primary responsibility at Cosmos. So to give a little bit of background, we are trying to design IBC to be a sort of TCP/IP for blockchains. If you think about the historical progression of computers, it was like the IBM PC, 1984, 1990. Eventually, all these computers became networked together thanks to Tim Berners-Lee at CERN. Although his was one of many competing proposals, it's hard to know how much path dependence there was. But thanks to Tim Berners-Lee, we were able to connect all these machines together with wires, and they became able to address each other. And ultimately now, when you go on Google or go on KakaoTalk, there's several layers of abstraction, but we're still talking over this basic fundamental network. There's several properties of TCP/IP that I think were important in determining its success in the web that was to come, and in facilitating sort of open and permissionless internet. All of this has now been come into question again because platforms on higher levels have imposed their own gateways. But one of the particularly important characteristics of TCP/IP, from my perspective, was that it was payload agnostic. TCP/IP dealt with, between computers, the addressing system, so how do you talk, how do you route packets, how do you get data from one computer to the other, and later on with TLS, how do you secure it so that you know that once you've established a ephemeral key pair between two computers over a connection, packets sent and received over that connection will only go to a particular destination, say a server owned by Google or a server owned by Microsoft, or a server owned by your friend if you set it up yourself. And then once that connection / channel is established, no one else can snoop in, intercept, see what's going on, or modify that. And we are aiming to design IBC as a similar sort of, to have a similar sort of role in the stack of many blockchains. We want IBC to be similarly payload agnostic, so it handles authentication, getting data from one blockchain to another, and transport, figuring out what kind of relay path, both between blockchains, but also between physical computers, where the data needs to go in order to, say, have a function call on one blockchain, get queued into an outgoing queue, sent over via some relays to another blockchain, I'll explain those terms in a second, committed on the other blockchain, maybe there are many hops, maybe just one. But IBC does not specify anything about the semantics of what that data means. So you can use IBC to send, in very simple manners, tokens, non-fungible tokens. You could use it to implement things like sharding as a layer on top of IBC. So you could have blockchains with consensus algorithms that maybe share validator sets, partially share validator sets, juniors would expect that, or don't share validator sets at all. Regardless, if they can authenticate each other's consensus algorithms, they can utilize the connection and channel primitives, which IBC provides, to send and receive messages, and then those messages themselves can translate into like validator set updates, which would allow you to do sharding. But you can further generalize to any sort of cross-chain contract call. So if you think about the EVM, in EVM, just because it's the virtual machine for contracting that most people are probably most familiar with. When you execute a call from one contract to another contract, you specify some call data, you specify the address of the contract you're calling, and then you basically dispatch authority. So the contract you're calling takes over, its code starts executing, you can call back into your contract, you can do something else. Calling back into your contract has caused a lot of bugs systematically, but it is possible. IBC can be used in a similar way, except that it's asynchronous, necessarily asynchronous, because the calls you're making are often going to be, in the interesting case, across blockchain. So you are going to say, I want to talk to this contract on this other blockchain, and there are secure ways you ought to specify what those identifiers are. Then you'll encode some data, maybe a method identifier and some call data if you want to invoke a method on a contract on the Solana blockchain and the Cosmos blockchain. Then that packet will get enqueued on the sending chain. So it will be written to the Merkleite state such that the receiving chain, which is verifying the sending chain's consensus algorithm, running a light client in the state machine, the receiving chain can check that that packet was enqueued, and then it can receive it only once and dispatch to the appropriate contract, which will execute the relevant logic and can send out the packets back or do whatever it might need. So if you think about if you were to write using IBC a smart contract as a logical entity, which in fact consisted of several different parts on different blockchains, you would need to write it in asynchronous style, which is like using promises in JavaScript or using a bit like using channels in Golang. You could think if you're using channels to communicate between Go routines, or like using actors in Erlang. Those are all basically the same. Channels and actors have an isomorphic transfer, I believe. So they're the same system from the perspective of IBC. And you could write that kind of really intricate cross-chain logic if you ensure that you can handle parts of your contract execution being asynchronous. That's what we think will end up being the future really interesting use cases of IBC. Initially, they will probably be more boring. It will consist mostly of sending tokens from the Cosmos Hub to the Iris Hub, or sending a non-fungible token from Ethereum through the Cosmos Hub to the Solana DEX, trading the non-fungible token for DAI, which also was transferred in a separate IBC transaction to the Solana DEX. Then the user who got the DAI, I got the DAI, maybe sold my CryptoKitty, and I want to withdraw that DAI onto Zcash so I can shield it and send it to June privately to buy some drugs. So I send my DAI over to Zcash, I shield it because I can use the unique features of the Zcash state machine, in this case the circuit, which allows you to ship tokens, or would in this future, doesn't that go soon. Then I would be able to send my Zcash to June, who would get them shielded on Zcash. Maybe he could then unshield them and send them back over to Ethereum. That would be what I would expect to happen in the next year or two with IBC. But in the far future, I expect that state machines will get more complicated, because in addition to the challenges with sharding a single blockchain insofar as scalability, data election, and sharding and resistant to bribery attacks go, the other difficulty is simply that different blockchains, a single blockchain with a single VM has a hard time supporting a wide diversity of use cases. If you think about the most useful kinds of features in blockchains, like circuits for zero-knowledge proofs, like some kind of really optimized low-level instruction sequence for a decentralized exchange that can be cached every block so you can run it really quickly. It's much harder to do that when you have to fit it all through the same virtual machine model, like you would if you use EVM, even like you would to a lesser degree if you use x86. If you use any single virtual machine and try to support these arbitrary state transitions like Ethereum, and try to be a world computer, you're kind of going to end up serving this. You're going to do an average job for every use case, but have a much harder time doing an optimal job for a single use case or a small set of use cases, maybe like shielding tokens, because different token denominations sending through a Zcash circuit is not really a different technical problem to solve, but having a Zcash circuit and DEX on the same blockchain, or in particular in the same state machine, is quite difficult. Even if you can integrate the code together, you now can no longer make the same assumptions about caching, about how you can store things on disk. You have to deal with uneven transaction loads across these different applications and running different ones or when. It's much trickier. And it means that whatever validator set you have is not necessarily going to be so well aligned to those particular use cases. So if you're operating a DEX, you might end up converging to a validator set where the validators are running front ends for the DEX or something like that. Or if you're operating a zero knowledge payment zone, you might end up with wallets running the proof of stake system. Maybe not. But if you're running all of these different kinds of applications on the same chain, it's hard to even try for that convergence. So I think we're going to see diversification of state machines across blockchains. And a lot of the design goals, many of the design goals for IBC are oriented with that in mind, such that we can support contracts, logical contracts, so things the user thinks about, what you would use by clicking a single button in an app, right? So the execution is, from the user's perspective, atomic, but which actually translates to a set of calls and state transitions across different blockchains, different consensus algorithms, and different state machines, which are each really well optimized for their particular uses. Cool. That was a lot of them. Questions?
2 questions. You mentioned both of the examples you brought up were transferring scarcity across chains.
Yeah.
Does the protocol then enforce this idea of burning tokens in one and creating a
The IBC protocol does not. So there are 2 layers you can think of. The layer that we're calling IBC or IBC core consists solely of transport and authentication primitives, ensuring that packets going from one chain to another chain get there, but only there, can't be masqueraded, can't be altered, and get there only once. And there are also some ordering constraints you can impose. But
is there guaranteed delivery?
Modulo liveness, yes. And not only liveness, but accepting the transaction, the usual thing. The second layer, which we'll also write specs for, but which you could implement the core protocol without implementing or with only implementing part of, will be specific packet encodings. And those specific packet encodings, which will describe the format of data, will describe, for example, the format of specifying token denomination and amount. And along with the packet encoding, they will specify what the state machine has to do in order to preserve particular semantics across the set of chains. So in this case, in the case of fungible tokens, when the sending chain sends tokens, it has to either burn or escrow, and when the receiving chain receives tokens, it has to mint or escrow, depending on the supply balance between the 2 chains. Similarly, for a non-fungible token, you always have to burn it.
So you somehow handle authentication that if I'm receiving a message that says create this this NFT representation of something in a different chain, I can somehow authenticate that and it was destroyed. Right, so it's not like a double.
Well, so the guarantee you get is similar to the guarantee you get with a light client of Solana. Without extra stuff, you're not authenticating the state machine. Now, you as a user can read what the consensus algorithm is doing and check that the state machine is only going to send this IBC packet if in fact it is burning coins. But
so is the Cosmos running the light clients, or the receiving both the receiving party has to run the light client state machine?
Both work. We expect, as in the protocol can handle both cases. So the receiving chain can run its own light client at the sending chain, or the receiving chain can basically dispatch the running of that light client to some hub, we call it a hub, like the Cosmos hub, and the receiving chain can only verify the Cosmos hub, and basically, when it verifies the Cosmos hub, it gets the latest states of all the other light clients the Cosmos has verified.
Got it. Okay.
Other questions? Was that demystifying? Was it more mystifying?
It sounds more like that more than a year away.
Oh, well, you might be surprised. You can look at the specs online. June's been writing the implementation, and the team actually used it at a hackathon about a week ago.
That's awesome.
It's not yet production ready, but it's close. We anticipate merging into them before the end of the year. The hope is really that IBC can serve as a standard. So it's not designed basically, at Tendermint Cosmos, we split our stack into 3 components and they're all independent. You can use Tendermint without using anything else. You can use the Cosmos SDK without using anything else. You can use IBC without using anything else. They all work very well with each other. Tendermint plus the SDK plus IBC, fit nicely. You can have properties like client verification on Tendermint that are quite essential for IBC. But you can use IBC with different consensus algorithms, different state machines, working with the theory to what it's going to do.
We could probably jump to the panel now. So there's like let's check validator panel. So I think so we're gonna have Anatoly moderate. Can I get Adrian up? One second. Yeah, Adrian. Both Adrians. Ryan, PoS one, and Julian.